All right, inverse functions. First of all, let's start with the definition of a function. It's there on your paper. You've been talking about functions for a while, but I just want to review the definition of a function. Each element of the domain is paired with only one element of the range. In other words, for every y, there's only one, or excuse me, for every x, there's only one y. That's where the vertical line test comes from. If we had more than one y value for a particular x value, that's where we would fail the vertical line test and it's not considered a function. Now, inverse functions switch the domain and range of a particular function. So the domain and range switch, so domains are x's, ranges are y's, so our x's and y's switch places for inverse functions. Our notation, we need to make sure we're familiar with that. It looks like a negative exponent, okay? It looks like a negative exponent, but it is not. That is our inverse notation right here. You read that f inverse of x. It's not f to the negative 1 of x, okay? It's f inverse of x. So let's look first of all at what we call a function map. That's what these are right here. On the left side are the set of x values. On the right side are the set of y values, and what this does is it draws an arrow from the x value to the corresponding y value. So if our function is the absolute value of x, if x is negative 3, the absolute value of negative 3 is positive 3. So you see that arrow going from negative 3 to positive 3. Well, positive 3, the absolute value is also positive 3. So forth and so on. We could go through all of those. The absolute value of x is a function, okay? The absolute value of x is a function because every x has only one y. There are not multiple arrows coming out of any of our x values. So it is a function, okay? Its inverse would switch the x's and y's. So I'm just going to put this right down here. I don't know what the inverse of the absolute value of x is in terms of the formula, but it would switch. So the first bubble over here would be the y values, the second bubble would be the x values. Is the inverse a function?
No.
No, because if this is our set of x values over here on the right, 3 has 2 y values. 2 has 2 y values. So its inverse is not a function. Okay, f inverse of x in this case is not a function. So in other words, if you are examining a function here and it has different x values that map to the same y value, then you know its inverse is not going to be a function. Okay, because when you switch them, then those x's are not going to have just one y value. Okay? Now, another function here, let's look at g of x. It's a linear function, x plus 3. If we look at it the same way, we've got x values here, we've got y values here. Each x only goes to one y, so g of x is a function. If we graphed it, it would pass the vertical line test. We can see there's only one arrow coming from each y value, or excuse me, from each x value. Okay, and if we were to talk about its inverse, switching the x's and the y's, the inverse would also be a function. So we call this specific case right here, when both a function and its inverse are functions, that is called 1, 2, 1, which kind of makes sense. Every x has only one y, every y has only one x. That is not the case in the case of f of x equals the absolute value of x. Every x has only one y, but every y does not have only one x. Okay? Absolute value of x is not 1 to 1. X plus 3 is 1 to 1. Okay? Let me go back to the inverse of the absolute value not being a function, it is what we would call a relation. Okay, there's still a relationship there between those y values and x values. It's just not a function relationship because it doesn't match up the way it's supposed to. All right, so let's look at some more graphs. Yes, sir. Did you have a question?
So like any kind of parabola, it's going to be not 1 to 1.
Right. A parabola, x squared, would not be 1 to 1. Okay. The parabola itself is a function. Its inverse is not a function unless what we're getting ready to talk about, unless we restrict the domain. So let's look. We've got 4 graphs right here. We've got a linear function. What's graph 2? What type of function is that? Anybody remember? Y'all got to start recognizing this.
Linear?
Graph 1's linear. What's graph 2? What's graph 2?
It's
Rational. Somebody remembered? Variable in the denominator, rational function. Okay, graph 3 is quadratic. I think everybody knows that one. And graph 4 is cubic / we'll call it a polynomial as well. Technically, the quadratic is a polynomial, but okay. So I just wanted to review that. That really has no emphasis or impact on this inverse discussion, but I did just want to review what those functions are because y'all still don't recognize rational functions. Okay, so let's look at these and let's talk about them one at a time. Which of the following graphs show functions that have inverses? Okay, which of the following graphs show functions that have an inverse? So graph number 1, would its inverse be a function?
yes.
Yes. Okay. Graph number 1, yes, its inverse would be a function. Okay, because every y value only has one x value. Okay, so here's a test for that. We've got the vertical line test to see if a function is an inverse. If you flip that line over and use the horizontal line test, it will tell you whether the inverse is a function. Okay, so graph number 1 passes both the vertical and the horizontal line test. It will touch the graph only at one place for both a vertical and a horizontal line. Graph number 2, is that rational expression there a function? Is graph number 2 a function?
Yeah.
Yes, it is. It passes the vertical line test. How about its inverse? No. Okay, it would fail the horizontal line test. For example, let's say at y equals 1, it's got -1 and +1. So it would fail that there. So 2, the inverse is not a function. How about 3? Is the inverse a function? No. Okay. It also fails the horizontal line test. Okay. If we talk about, I'm trying to pick an even one here, 15. Y equals 15. We've got -1 over here, and we also have +7 over here. So every y does not have only one x value. Okay, how about number 4? No, it also fails. This is actually a good example. When we talk about 0, it's got -2, 0, and 2. It has 3 x values that have a y value of 0. So the only one right now whose inverse is a function is that first graph, the linear function. Okay, all the other ones, their inverses are not functions. It's not that they don't exist, they're just not functions. So let's look at B. It says for each function that does not have an inverse, can we restrict the domain so that it does have an inverse? Okay, can we restrict the domain so that it does have an inverse? So in other words, is there symmetry here so that if we took away half of the graph, we would still get all the same y values, but we wouldn't be repeating them, okay? So what I mean by that is on number 2, if we cut it off right here at 0, if we ignored the left side of this graph, the left side and the right side are mirror images of each other, okay? So I'm not losing any y values if I remove the left side of this graph, But if I take away the left side, would the inverse then be a function? If I didn't have the left side right?
Yes.
It would. Okay, it would, because then it would pass the horizontal line test because I don't have that repeating there. So if we said x was greater than 0, that would restrict our domain. We would be ignoring the left side of the graph, but we wouldn't be losing anything. Okay, we would not be losing anything, but we would get rid of the problem, so to speak. Okay, could we do a similar thing with number 3? Yeah. Where would that change? Would that change at 0? Should it be the same place? No. Okay. At 3, okay, if we cut it off at 3, we would get rid of one side and we would remove the problem. We could do x is less than 3. There's nothing that says we have to consider the right side. Okay, we just favor the right side because we like positive numbers. Okay, but there's nothing that says we have to do the right side. So I just wanted to show you the possibility that we could restrict it to x is less than 3, so we would consider the left side of our graph right there. Can we do that to number 4?
No.
Okay. Number 4 does have some symmetry. Okay, it does have some symmetry. What kind of symmetry does number 4 have? Does anyone remember what we call that? What type of function is this?
Cubic.
Okay, it's cubic, but even, odd, neither. It's odd, okay? Odd, remember, has rotational symmetry. So there is symmetry here, but we need to have even-like properties in order to restrict this domain. Let me show you. If we cut this off at 0, okay, and we just consider the right side, look at what we're losing. Okay, we're losing all of this right here, and this part of the graph right here. We don't have that on the right side. Or if we took away the right side and we only considered the left side, we're missing all this stuff up here in the top right corner. Okay, so we cannot restrict the domain of 4 to make its inverse a function. Okay. All right, that's going to come into play here in a minute. So we talked about determining whether an inverse is a function. Let's look at actually finding an inverse. Okay, let's look at actually finding a rule for the inverse. Here are your steps. We're going to switch x and y in the equation. We're going to solve the equation for y, and then finally at the end we're going to replace it with the inverse notation. So let's look at what are all the functions in example 1 here. What type of functions are those? Linear. Okay, so we're going to look at linear functions, and we're going to find their inverses. Okay, so A, g of x is equal to 3x. We switch x and y. Well, I don't see a y in the equation. G of x is just a fancy way of saying y, right? That's function notation for y. So we replace that with x. We replace the x on the right side with y. We're solving for y. So what do? Divide both sides by 3. So we've got x over 3 is equal to y. We've got y by itself, so we replace it with the inverse notation. I prefer that to be on the left side of the equation, so I'm just going to flip it around. You can write that as x over 3, or you may see it as 1/3 times x. You just need to recognize that those are equivalent to each other. Okay, so there is our inverse rule for the inverse of 3x. So the original was linear. What's the inverse? It's also linear, isn't it? X is in the numerator. Rational only applies when the x is in the denominator. Okay, we don't have an x in the denominator. It's a little bit more obvious with the 1/3 x to recognize it as a linear function as opposed to the x over 3. Okay, let's look at B. H of x is equal to 3x plus 5. Replace the h of x with x, replace the x with y, and we're going to solve for y. So what do we need to do first? Subtract the 5. So we have x minus 5 is equal to 3y. Then this is just like the previous problem. We divide both sides by 3. So we have x minus 5 over 3 is equal to y. Let's replace that with the inverse notation. H inverse of x is equal to, you can leave it like that, x minus 5 over 3, or they may split it up. So that's 1/3 x minus 5/3. It's just putting both terms over 3. So 1/3 x minus 5/3. Again, linear original function, linear inverse function. Okay, let's look at example C. J of x is equal to 3x minus 7. Replace the j of x with x, replace the x with y. Solve for y. So we add 7 this time. X plus 7 is equal to 3y. Same as what we've been doing. Divide both sides by 3. X plus 7 over 3 equals y. So replace it with the inverse notation. J inverse of x is equal to x plus 7 over 3, or 1/3 x plus 7/3. Okay, one more. I know these are pretty simple, but I want to point something out with this last one that I want y'all to get in the habit of doing. We've got x is equal to 3 over 5y plus 4. Nothing different happening here. Subtract the 4 first. X minus 4 is equal to 3 over 5y. How do we get rid of the 3 over 5? Lovely. That's exactly what I wanted to hear. We multiply both sides by 5/3. I want y'all to be in the habit of when a fraction's involved, to move it to the other side, you multiply by the reciprocal. Okay? Yes, you can look at it as division by 3 over 5, but it's a lot easier to deal with if we look at it as multiplication by 5/3. Let's distribute that 5/3. So 5/3 x minus 20 over 3 is equal to y. So k inverse of x is 5/3 x minus 20 over 3. Okay, so linear functions have linear inverses. Okay, linear functions have linear inverses. Let's look at the next type of function. Okay, so we're going to step up from linear to nonlinear. Okay, parabolas, quadratic functions, parabolas. Okay, we're going to find the inverse. Now, notice I've got a little something extra beside each of these equations. Okay, it's not just f of x equals x squared. There's something in parentheses. For x is greater than 0. What we're doing is we are going to go ahead and restrict the domain so that we're only looking at one side of this parabola so that its inverse will be a function. Okay, so I'll show you where this comes into play here in a second. Same process as before, nothing changes. Anytime you're finding an inverse of any function, you switch x and y. The only thing that's different is what steps you have to take to get y by itself. Okay, that's what's going to be the difference, is what steps do I have to take to get y by itself. In this case, what do we have to do to get rid of that squared? Square root. Okay, what are we supposed to remember when we take a square root? Positive and negative. Okay, but here's the problem. If we include the positive and the negative, I'm going to leave it off for this moment. But let me show you. If I graphed that, we've got y by itself. Okay, let me get this stuff out of here. If I graphed both the positive square root of x and the negative square root of x, look at what will happen. Okay, I'm not able to put the plus or minus in my calculator, so I have to put it in separately. Is that a function? No, it's not a function. But if I just graph one of them, is that a function? Yes, that is a function by itself, just the positive square root. So here's where that inequality comes into play. It says for x is greater than 0. So when x is greater than 0, is that positive or is that negative? It's positive. Okay, so we are only going to consider the positive square root of x for this inverse function right here. Okay, we are only going to consider the positive square root of x for this function. Okay, so let's do another one. Let's look at b. F of x is equal to x plus 3 squared for x is less than negative 3. Okay, less than is going to imply negative. Okay, less than is going to imply negative. So when we switch x and y, what do we need to do first here to solve for y? Square root. Okay, we're going to take the square root. But this time when we take the square root, we do want the negative in front of it. Okay, we do want the negative in front of it. So we've got the negative square root of x is equal to y plus 3. So we've got to subtract 3 to get y by itself. Now be careful with this. You cannot put stuff under a square root unless it was already there. Okay, so when you write f inverse of x here, it is the negative square root of x. Notice I put that little, I don't know what you want to call it, cap, so to speak, on the end of my square root. So it is clear that that minus 3 is not under the square root. It comes after the square root. We just talked about transformations, right? It makes a big difference whether that minus 3 is under the square root, that's a horizontal change, or if it's outside the square root, that's a vertical change. Okay, so make sure that you make sure that's clear when you write it, and make sure that you put the parenthesis in the right place when you put it in your calculator. Okay, let's do another one. Okay, this one looks a little bit different. It's still a quadratic, but notice how it compares to b. That squared is in a different place. This inequality says x is greater than 0, so that is positive when we're going to do the square root. So x is equal to the negative y squared minus 5. What do we need to do first on this one?
Add 5.
Add 5. Okay, we cannot take the square root until that y squared is by itself. So we're going to add 5 first. X plus 5 is equal to negative y squared. Okay, we cannot take the square root yet because y squared is not by itself. We've got to divide by negative 1. Dividing by negative 1 changes those signs on the left side, both of them. Okay, it changes both of them. So we have negative x minus 5 is equal to y squared. Finally, we can take the square root. We are only considering the positive, so we have g inverse of x is equal to the positive square root of negative x minus 5. Now, what's under the square root doesn't have to be positive, okay? The only thing that positive tells us is that it's the positive square root. Yes, sir?
So I imagine you can just do it like that. But what if you took out like an imaginary and say x plus 5? Can you do that?
Mathematically, yes, but we don't graph with imaginaries, so we're just going to leave it the way it is. But way to connect the imaginary and factoring, and I love it. But we don't graph with imaginaries, so I mean you can, we just don't do it. Okay, let's look at h, or h of x. Okay, example D, h of x is equal to 2x squared plus 4x minus 1 for x is less than negative 1. So, first of all, negative square root, because it's less than. Okay, when we switch x and y here, can we isolate y when it looks like that? No, we can't. I've had lots of people try, but you can't because you have y squared and y. We cannot get y by itself in this form. But what we can do is what we looked at yesterday. Can we write that in vertex form? Yes, we can by completing the square. You may not remember, but we can. So we got to start by factoring out that 2 and leaving that -1 outside of our parenthesis. Okay, when we complete the square, 2 divided by 2 is 1, 1 squared is 1. Okay, but we had that GCF in front, so really we just added 2 to our equation, so we have to balance it by subtracting 2 from the end. So let's put it in factored form. 2 times y plus 1 squared minus 3. Can we get y by itself in this form?
Yes.
Yes, we can. Okay, we can. So let's do that. Start by adding 3. We've got x plus 3 is equal to 2 times y plus 1 squared. The squared expression is not by itself yet, so we have to divide by 2 first. X plus 3 over 2 is equal to y plus 1 squared. Now we can finally take the square root. And we're supposed to consider the negative square root for this one. So negative square root of x plus 3 over 2 is equal to y plus 1. And we got one more thing to do. We got to subtract 1 from both sides. And that's not under the square root. And I don't feel like writing it again, so my inverse is just going to be on the right side of my equation, and that's okay. It doesn't really matter which side it's on, just so it's there. Okay, so that one's got a little bit more to it than the other ones that we've done. Okay, but I wanted to put this one on here because I have had so many people in the past that have tried their darndest to solve for y in this form right here. You can't do it because you got y squared and y. You got to break it down. You got to rewrite it so that you have just that single y right there. Then you can solve for the inverse function. Now, let me show you something. At the beginning of this, I was showing you those function maps to show you the relationship between functions and their inverses. Let me show you another property of functions and their inverses. So what I'm going to do in my calculator is I'm going to graph this original function, 2x squared plus 4x minus 1. And I'm going to put in its inverse, negative square root. Now, be careful with this. X plus 3 needs its own set of parentheses. Okay, that parenthesis right there is for the square root. I got to put x plus 3 in parentheses, divided by 2. Then I can close parentheses, because that's the only thing that's under the square root. The minus 1 goes on the end. Okay, I'm going to put one more equation in here. I'm going to put the line y equals x. And I'm going to press zoom number 5 for square. And that's because if I just have a typical negative 10 to 10 window in both directions, our screens are wider than they are tall. So the x values are actually stretched out more than the y values. If you square it, what it does is it makes the x values be the same distance apart as the y values are. Okay, so we actually have a few more x values than normal. Okay. What I'm trying to show you here, with this line, y equals x, if you turn your head so that that line, y equals x, is straight up and down, can you kind of see that the left side of this parabola, if we flipped it over that line, would give us that square root function that we graphed. Okay? That is another property of inverse functions. They are reflections across the line y equals x. And that has to do with the fact that the x and the y values switch places. Okay? The x and the y values switch places So they are reflections across this line y equals x. We only consider the left side of this, okay, because it was x is less than -1. Okay, we ignore that right side, and that is a reflection right there. If that inequality was flipped around, if it were the positive, okay, then we would ignore the left side. Okay, we would ignore that part of it. And the right side and the square root are reflections across that line. Okay, so we're going to continue with this tomorrow. I do have a couple more things to say, so hold the papers for just a second. You need to be able to find an inverse by just switching x and y values in a table, which we will look at a little bit more tomorrow. You need to be able to find an inverse algebraically, like we were just doing. And you need to be able to recognize inverses when you're looking at the graph with that symmetry across the line y equals x. We'll work with all three of those more tomorrow, but you do need to know those